Hi, my name is Pierre-Yves Ricau. I'm a software engineer at Square. And today I'm going to talk about Shark and diving into the guts of LeakCanary's Hprof parser. So I also have stickers. So the stickers here, if you're interested in getting a LeakCanary sticker, talk to me after the talk or anytime during the conference, and I'm happy to give them away to you. So I guess I'm going to do kind of show offhand how many people have used LeakCanary before. I'm assuming you're here because you know what it is, because otherwise it's kind of a weird talk to go to. So let's see. A couple months back in April, I released LeakCanary 2. And so it was a complete rewrite. We rewrote everything to Kotlin, but we also rewrote the Hprof parser. And so there's essentially a new heap dump parser, and it's called Shark. And so Shark stands for Smart Heap Analysis Reports for Kotlin. I really wanted to use Shark as an acronym, and so I had to figure out a way to make it fit in. So essentially, it's the same as before, but rewritten from scratch and way faster and way less memory. It also comes with a command line interface, which I don't know if you can read from here. It has a nice ASCII art thing, but you can also run commands where you can ask the command line from your desktop to run the LeakCanary analysis on an app that doesn't even have the library. So it's pretty interesting. It's getting kind of different. So today we're going to look into what's inside Shark, and hopefully we're going to learn a few things from that. So I guess the first question is, what is a heap dump parser? What is that doing exactly in LeakCanary, right? So we have to talk a little bit about how LeakCanary works. So since V2, essentially the way you use it is all you do is you add a dependency, and that's it. It works out of the box. You just add a dependency. You don't even have to write any code, and it just works. It's using a content provider hack to bootstrap itself on App Startup. And then what it does is it installs an activity lifecycle callback on the application class. And whenever an activity is destroyed, it passes that instance to an object watcher. And what the object watcher does is it creates a weak reference to the activity instance. And that weak reference goes into a reference queue. And then if after a while, if the weak reference isn't clear, the object is considered retained. And when that object is considered retained, we call an Android API, which is a pretty cool API that's called debug.dump_hprof_data. And that actually calls into a native API behind the hood and under the hood. And that actually copies the entire memory of the entire heap of the VM into a file. And that's called an Hprof or a heap dump. That's the same thing. If you're actually curious about how it's actually happening within your process in the native code. And there's this file, hprof.cc, that has all the details about how that's happening. It's not very useful for your day-to-day development, but it's kind of cool. So after that, LeakCanary, the heap parser, will parse that file, and that's what we're going to talk about today, and output the LeakCanary result that you know. And then you can use that result to find your leaks, or maybe you find a leak in AOSP and you submit a ticket, and maybe someday it will be fixed. We're hoping for that anyway. So let's talk about how heap dump parsing works and how we can find memory leaks. But to do that, we have to talk about garbage collection. So who has some vague idea of how the garbage collector works? Oh, great, everybody. I don't really need to talk about this then. Let's get into some of the details. So the best way to explain garbage collection is to read Wikipedia. So in computer programming, tracing garbage collection is a form of automated memory management that consists in determining which objects should be deallocated, garbage collected, by tracing which objects are reachable by a chain of references from certain root objects, considering the rest as garbage and collecting them. it's interesting because tracing garbage collection is the proper word. There's other ways to do garbage collection, like reference counting. I think it's an iOS thing. We have it way easier with our tracing garbage collection. Just magic, right? Wikipedia also has this really nice GIF, which shows how it goes from the root and then explores the graph of objects through the reference between objects, right? And then everything else gets, everything that hasn't been marked gets swept. It's the mark and sweep algorithm. You may have heard that before. So that's cool, but then the next question is, well, what is a GC root? We keep talking about that, right? And Wikipedia, again, a distinguished set of roots, objects that are assumed to be reachable. So essentially they're saying it's variables on the call stack and global variables, so static fields. The most common one is static fields, and that's why if you put an activity in a static field, guess what? It's not going to be garbage collected, right? And then you have an activity leaking. Okay, thanks Wikipedia. So we know how garbage collection works. In practice, it's a little bit more complicated than that, but it's kind of the general idea. And if a heap dump is a copy of the memory, the heap dump really sees the same thing that the garbage collector sees. So what we're going to do with our heap dump parser is going to be very similar to what the garbage collector does with the live memory. And essentially, so this is a graph that represents something in memory. At the top, you have a bunch of garbage collection routes, and then they have references to objects. We have references to other objects. So in purple arrows are those references. So if we were to run a mark and sweep, the GC would mark all of the objects, and the other ones would be swept because they were not reached from the roots. So that's cool. Now, the GC went through, it garbage collected everything. That's really cool. And then turns out one of these objects that is referenced is an activity that has mDestroy true. It's a destroyed activity, but it wasn't garbage collected because there's a reference that's reaching it, right? It's a reachable object, but we know that a destroyed activity should not be reachable. It should be garbage collected. And that's where LeakCanary comes in, right? We had a weak reference to the activity, so we know it should have been garbage collected, and it wasn't. So we make a copy of the memory, and now we need to find the path from the roots to that activity. So we want to find why this instance is kept in memory. And to do that, we really have to do exactly like the garbage collector. We have to traverse the graph of objects. So here, if I was to ask you, if you look and you're like, well, why is this object still in memory? Your brain is actually really good at doing path finding, and it would immediately tell you, well, you go from here, and maybe you take that arrow, and that's how you get here, right? So we can do that in code, and it's not that hard. Our brain aren't that smart anyway. It turns out that here I try to draw all of the paths from the GC roots to the object, and you can see that there can be many. In practice, we could look at all of the paths, but we only care about one. It doesn't really matter which one. We know that if there is a leak, the leak is going to show up on all of the paths. So we pick one, and what we do is we pick the shortest, simply because it's less information to look at. So let's pick the shortest one. And this is kind of what LeakCanary shows you. On this side, you see the typical LeakCanary UI, and on that side, that's kind of the representation that I had. One of the interesting things is that LeakCanary also runs some heuristics to tell you, I think this object is leaking, this object is not leaking, which helps it understand which parts, which references are potentially bad. So you can say, well, here is the path, but actually I know this and this are probably where the problem is. Cool. So now we know what the heap analyzer in LeakCanary does. So let's talk about heap parsing. When I say heap analyzer and heap parsing, I mean heap parsing is like parsing the file, and then doing the smart stuff on top is kind of the heap analyzer. So if you've used Android Studio, okay, who's used the memory profiler in Android Studio? Like those nice, beautiful charts. Wow, everybody, that's amazing. So there's a button there. It doesn't look like much. It's kind of a square with an arrow, and it means dump the heap. And what it does is what we talked about, copy the memory heap into the Java heap into a file. So you can do that. And if you do that, you will see this, which is kind of useful, but not really. But that's what Android Studio provides you with to analyze that memory. And what's happening under the hood is they have their own heap dump parser, and that's what's used to represent that information. What's really interesting here, and something that I encourage you to look at, is the columns. So allocation is the number of objects that exist of that specific type. Shallow size is so this is a sum. So you have to so basically every object in memory has uses a chunk of memory, right? I need 8 bytes for a long, I need 4 bytes for an int. And then you do the sum of that, and that's the shallow size of that object. And then here they multiplied it by the allocation, so you have 6 megs of object arrays. What's way more interesting is the retain size. So let's talk a bit about that. So I zoomed in on the graph that we had before. The retain size, this is Wikipedia again, I think. Or maybe some other website. Retain size of an object is its shallow size plus the shallow size of all of the objects that are accessible, directly or indirectly, only from these objects. In other words, the retain size represents the amount of memory that will be freed by the garbage collector when this object is collected, right? So here, if we remove the reference from the top, all of a sudden this is isolated, it all gets garbage collected, and we would reclaim 6 times 32 bytes. I don't know how much that makes, it's too hard to compute. So yeah, it's some of the shallow size. And so what's kind of interesting here is that how do you compute retain size, right? Well, it's something called dominators. It's kind of an interesting word, but you do what's called computing dominators. And essentially what you do is for each object, you try to find which objects you have to go through to get to it, right? And if I have another object, if I have a first object and a second object, and you have to go through the first object to get to the second object, then the first object is a dominator of the second object. And so I can take the shallow size of that second object and add it to the retain size of the first object. So that's interesting because it's going to tell us a lot about where our memory problems are, which is what we're going to dive into in a little bit. So if we look back, so this is the thing that's in Android Studio. When this came out, I realized that this was a heap dump parser, and I needed one for LeakCanary. And so this is backed by a library called Hprof, which lives in AOSP. So I essentially repackaged it and called it heap. What is it? Headless Android Heap Analyzer, short for HAHA. And yeah, I like good library names. And it worked really great. And I didn't have to write a heap dump parser, so that was amazing. I just had one out of the box. It just had one little problem. Out-of-memory error. We kept having people reporting out-of-memory errors on big heap dumps. We also had the same issue. So let's dive in. Let's figure out why we have an out-of-memory error with our heap dump parser that's supposed to help us prevent out-of-memory errors. It's kind of ironic. So what I did is I wrote an instrumentation test. I took 2 Hprof files. So those are, again, copies of the memory. There's a large dump and a huge dump. One of them is 40 megs. The other one is 160 megs. And then let's start the test and run the profiler. So you probably have noticed this if you've tried to profile a test. There's no way to say, well, there is an entry that says profile this test, but the test is not going to wait for the profiler. So by the time the profiler initializes, the test is already done, and it's kind of like sad. So the way we work around that is through thread.sleep, and that way we have enough time to hook up the profiler. Great hacks. Okay, so for the large dump, so let's see. This is what I got. So you can see it's kind of like analyzing. It's parsing the heap dump, and then it's going to start analyzing it. So here you can see there's about, you cannot see probably because it's too small, but there's about 140 megs of Java memory used, and 180 total. There's other. There's about 40 megs of other memory. I may talk about that in a minute, but essentially you're like, that's already kind of a lot. Okay. Before we go into other things, I wanted to mention there's a new benchmark library from Google that's supposed to be really good for these kind of things, or at least benchmarking and performance tests. The problem is that it does two things. It warms up, it basically logs the CPU so that it's always 100% and it's constant and you don't have variations there. And then it runs the code as many times as necessary to make sure that there's no statistical difference. The problem is as many times as necessary is a lot of times, and LeakCanary takes about a minute or two to run. So if you try to wait for it to run, I don't know, 10,000 times a minute, like nobody has time for that. So you can't really customize the duration. So the benchmark library sounds useful, but hasn't been useful to me, I guess. Another library worth mentioning is Nanoscope, and I just completely forgot to look at it. But it's essentially a modified version of Android. It's like a specific emulator that has the ability to do performance measurements without overhead, because it's directly in the OS, and that's pretty cool. Okay, so let's look at the huge dump. All right, so same kind of deal, except now what I'm reading is 350, 400 megabytes, and 550 total. And that goes for about, it's accelerated, of course. We're not going to wait all day. It goes for about 4 minutes. And then it goes up and it stops. You're like, cool. Did it take 4 minutes and 500 megs to succeed? Well, if you look at the logs, you realize that what it's actually doing is just running the GC all the time until it says, I got an out-of-memory error. And then the actual error is, I got an out-of-memory error trying to throw an out-of-memory error. So I can't even give you a stack trace. So that's sad. I was like, OK, cool. I'll try to open. So in Android Studio, you can save the Hprof files, and then you can re-import them later. So I try to open that same huge file into Android Studio. This was the memory before. So that's like the baseline. It's using about 600 megs. Then it opened it. I waited. And then it was done. And I have about 2 gigs of memory used just to parse and analyze that 160 megabytes Hprof. So I was like, oh, that's a lot. So let's start doing performance optimization and focusing on the memory side of things. So we're going to take a heap dump of our heap parser, and we're going to start analyzing that. It's kind of meta. So how do we do that? Well, here I just, again, put a thread.sleep, and that way the thing was waiting at the right time, right after parsing, and I could click the little button and get a heap dump. Except I did not import that heap dump in Android Studio, because Android Studio, well, it gives you like a list of classes and their size, and that's it. There's nothing else that, as far as I've been able to explore the tool, I haven't found a lot of useful things. There's another tool called YourKit, which is kind of old, but works really well. Unfortunately, it's not free. You have to pay for it, get a license, or if you're doing open source work, they give you a free license. So I did that. I imported it into YourKit. And I opened this view called the top dominator. So now you know what a dominator is. It essentially tells you where the objects that if they were garbage collected, you would reclaim the most memory. And here it's telling me, well, 94% of your memory would be reclaimed if that object was garbage collected. And that's the snapshot, which is essentially the object that wraps the parsed heap dump. So that's cool. And then we can say, hey, YourKit, show me, for that one object, show me the composition of the different types that it's holding, not just directly, but also transitively, to kind of understand what the memory is made of. And here, we can see that there's about, so I kind of, there's again 2 columns. This time I sorted by shallow size, because what I'm interested in is the row size of every type accumulated by the number of instances. So I can see I have 125 megs of class instance. And class instance is essentially, so what's going on is this in this heap dump is that it was taken, there's 2 heap dumps here, right? There's the one that we're looking at, which is of the heap dump parser, and there's the heap dump that the heap dump parser was parsing. So I'm talking about that other one. It was parsing a heap dump with about 1.4 million objects, and that used about 125. Just those are just the instances of class instance, which represents, it's like object in Java, but in the heap dump world. That was 120 megs. Then there's array list. It's using about 80 megs. Array is instance, which wraps an array, is about 70 megs. So you can see it's kind of a lot. And we have a lot of, essentially it's a heap dump with a lot of objects, and therefore it's overall using a lot of memory. One of the interesting things with array list is the shallow size is very close to the retain size. We see 80 megs of shallow size, 115 megs of retain size. What's actually happening here is that every single class instance has creates an empty list, and it keeps a reference to an empty list. And so you have 1.4 million empty lists. And so just like these things add up when you're looking at millions of instances. And this is what a class instance looks like. And so you can see there's a bunch of fields. And so now we get into how much memory does my object use? And that's always interesting. So in Java, the answer is always it depends, right? And in this specific case, it depends. But essentially, on a 32-bit VM, the object in memory will use 12 bytes for the header. So that's going to be a reference to the class, a bunch of random things that are in there. And then 4 bytes for every reference. If it's a 64-bit VM, it would be 8 bytes. So here, if you did the count, you'd end up with 88 bytes. So every class instance is taking 88 bytes. Multiplied by 1.4 million, that's a lot of megabytes. As I was looking at this code, I noticed that one of the interesting things about class instance is that it does not actually hold the list of fields and their content. It holds a pointer into the file. This is this mValues offset. And when you try to read the content of an instance, it actually goes to that file and reads that. And I thought that was an interesting idea that we could take further and essentially remove a lot of the data in class instance and a bunch of other objects and just keep the pointer and have a map of an object ID to the pointer in the file. And that way, when we need it, we just go in the file, read it, and hopefully it uses way less memory. So to kind of understand how we are going to use that, we need to talk about what LeakCanary does next, like finding the path from the GC roots to the leaking instance. So we're going to do something called a breadth first search, which is a scary name that resonates like, oh, you're about to do a Google interview. But it turns out, no, and it's not that hard. So we're going to get through that together. The general idea is that we're going to have a queue, first in, first out queue. So what's a queue? It could be an array list. It's just it's just an array of things, and you put things on one end, and you take things from the other end. And what that queue will contain is it will contain the temporary paths that you're building as you're exploring the graph. So we're just going to go, and we're going to put the GC roots in that, and then we're going to take the first GC root out, and we're going to say, well, okay, where do you go to? What are the things you point to? Okay, we're going to take those things, create a new path that has those new things on top, put that back in the queue, pop up the next thing, which is another GC root, etc., etc. And progressively, the queue will contain longer and longer paths until we find the instance we're looking for, and then that path is what we need. So let's get into actual code. So we have a reference path node. It's what is that? Well, it's just a thing that holds an object ID. And then, so it's a sealed class in Kotlin, and it's got two subclasses. One of them is root node. It's just the object ID. And then child node is a node that has a parent. And so a path is essentially a child node that points to a parent node that points to a parent node that points to a root node. And so how do we do this? It's really, really not that hard. We create an array deck. Think of it like an array list. It's a double entry queue that is backed by an array, and a hash set of what we visited, so that we don't keep visiting the same nodes. Otherwise, we're just going to turn forever. And then like I said, we enqueue the GC roots. So we go over every one of them, and we put them in the queue and in the visited list. And then while there's stuff in there, in that queue, we keep going. And what we do is we get the entry at the top of the queue, and we say, is this the thing I was looking for? Yes? Okay, well then I have my path. I have this child node that's pointing to a parent node, pointing to parent node, etc. If not, then I'm going to read that object, get its references, and the references that it points to, and I'm going to add each one of them if I haven't visited them yet. I'm going to create a new node that points to the parent node, and I'm going to put that back in the queue. If I went through the queue and there's nothing left, then I couldn't find the instance. There's no pass, and that's it. We just did a breadth first search, and if you understood that with all the noise, and you're tired from your lunch and all of that, then you're ready for. I don't know if you're ready for the Google interviews. You're ready for the Square interviews for sure. Just throwing that out there. Who studied breadth first search or saw it before? Like, is it something that's kind of good part of the room? Cool. So okay, we know we only need like a map of an object ID to its position in the file, and we realize that perflib is reusing way too much memory. So we're gonna need to write our own heap dump parsers. And I think it took me about 3 years not doing it. But for 3 years, I was like, I don't want to do it. Until I finally caved and I started looking. And so I was like, I'm going to look at the spec of how the Hprof format works, right? It's going to be nice and very well detailed. And this is the spec. It's an HTML file from the 90s. It's kind of long. It's got a lot of things in there. So if we kind of dive in, they tell you, okay, so at first you have a string that represents the version, and you basically have a bunch of characters until you have a 0, and that's when you know that it's the end of the string. Then you have the size of identifiers. So like I said, on 32-bit, I don't know if I said that. On 32-bit VMs, a reference takes 4 bytes. On 64-bit VM, a reference takes 8 bytes. And so this tells you, well, it takes 4 bytes or 8 bytes. Actually, supposedly you can have 2-byte references or any number, which is kind of insane. And then we don't care about number of milliseconds, whatever. And then essentially, what's in a heap dump is a tag that says, here is a record of this type, and then the length, like how many bytes it's going to be for that record, and then the contents. So it's just byte arrays. And in there you have stuff like strings. So these are not your java.leg.string that you have in your program. They're actually strings that are the names of the classes and the names of the fields, and only that. And you have things like load class, which is just essentially a map from a class ID to a string ID, so that you can associate a class with its name. You have things like a class dump, which contains the details of the class, but it does not have an ID for the string that's the name of the class. So you have to find the load class, the class dump, and the string ID if you want to know the name of a class. And the details of the static fields and how many bytes they use and that kind of stuff. Okay, so that's kind of cool. And this is primitive arrays. So we can get started. So to kind of help you visualize what this is about, I rendered it. So this is an Hprof file. Obviously, it's super useful that way, and I'm sure you can totally understand it. So I'm not going to go into details. It's so obvious. So I'm just kidding, but I'm still not going to go into details. This is a feature that I did in LeakCanary, and there's no good reason for it. I just found it cool to be able to visualize what the Hprof looks like, and it's the different types of records that are in the file. So how do we parse a heap dump? Well, we're going to use Oki.io because Oki.io is amazing, and also it's actually fairly easy. I have a file, I have this Kotlin extension method that gives me an input stream. So far, so good. And then Oki.io provides other extension methods on the input stream to get a buffered source, which is essentially something that reads in chunks. So, okay, I got that. I need to read that string. So we basically locate the first 0, and everything that's before is the string, the version of the name of the version, and then the name of the type of Hprof. And then we skip 1 because we want to skip that 0. Then we read an int, okay, to know the size, if it's 4 bytes or 8 bytes for references. The timestamp, so far so good. And then we essentially just loop on the source until there's no bytes left. We read a tag. And so this looks like magic. I wrote this code, but I did not quite understand it because I was copy-pasting things. So I sat down to understand what I was doing. So what are we doing? What's happening here is I'm trying to read a tag, and the tag is an unsigned byte. Unsigned means there's no bit for the sign, so it's only positive. But Java does not support unsigned types. So when on OKIO I call read byte, it reads all the bits and returns me a byte, but its representation is a signed byte and not an unsigned byte, which means it doesn't actually correspond in terms of value. So we're going to convert it back to an unsigned byte by putting the byte into an int. So let's see how we do that. So imagine that I had in my file, I had those 8 bits, and it's an unsigned byte that represents 214. When I do read byte, I get the same bits, but it's now minus 42. Because Java is like, well, you have the sign bit is set, so this is a negative number. Okay, cool. So then I call 2 ints on it, and it's the same exact value, except it's in a bigger type, and so now it's like a bunch of ones. And then I do an AND, and essentially, so 0xff is a bunch of zeros and then 8 ones. And by doing an AND with that, it erases the first 3 bytes, and now I have my original number. So this is how you can, turn a, kind of like turn a byte into an unsigned byte into a bigger container. So we're going to skip some memory. We're going to read the length, and then essentially there's code like that goes on. It's like, oh, this is a string, so we need to read based on the size of the identifier. Maybe I need to read a byte. Maybe I need to read a short, because there's going to be more. And then here's the string length, and I'm going to read the string. So I'm kind of moving forward on that. But with that, we can read all the Hprof records and build an index. And with that, we can have a silk class that's going to be like index objects. And it's going to have the position in the file, and you're going to have a map of object ID to position in the file. And then you can have different subtypes, one for instances, one for classes, and you can imagine how we can add metadata that we care about, but skip the rest and keep the types small. Okay, so we have this silk class, that's cool. We create indexes. Essentially, there are maps of like, for this object ID, here's the data, here's the object, and then in there, there's also the position, so I can go and read more about it. And then we need to move around the file, so we essentially use Java and I/O. I didn't know how to do that, but it turns out it's also really easy with OKIO. You take your input stream and you get a channel from it, and that's a Java and I/O thing. And then you position the channel to a different position, and then you just tell OKIO to clear its current buffer, and now you're ready to read again from a different position in the file. Okay, cool. So been putting off that off for 3 years. I wrote the thing, and it turned out not to be that hard, so I was really happy, and I was like, how good are we doing now? So I ran the memory profiler again, and this was on the large dump, and it took about 4 seconds instead of a minute. It was really fast, and it used 30 megabytes. Then that's not bad, because before we were using 180 megabytes, right? So I was like, oh, that's really cool. What about the huge dump? It also took less time, still quite some time. What's interesting, though, is so before we were going and then crashing with out-of-memory error. So I had no idea. And Android Studio was using 2 gigabytes, so I wasn't sure how much it would be using. And here we're back to about 250 megabytes of cache and a bunch of other things. And the thing is, on Android, that's still too much. So I started looking. Let's do a heap dump and look again. What do we see? So if we look in, we see that this index that we have, those maps, they're still taking 240 megabytes. Okay, what's that made of, right? What's the composition? Oh, the top object is hashmap entry, linked hashmap entry. And there's about 87 megabytes, and there's 2 million of those. So also it's linked hashmap, because when you call mutable hashmap, mutable mapof in Kotlin, you get a linked hashmap. Which the difference between hashmap and linked hashmap, a linked hashmap is a hashmap. The main difference is that linked hashmap keeps the order of insertion. So when you read through the entries, it's going to iterate in the same order that you added them to the map. we have about 2 million longs. And so we're not talking about the primitive type, we're talking about the wrapper type. So a long is 8 bytes, but the wrapper type is like, wait, what is it? So it's 12-byte header plus the 8 bytes, right? So here, we would normally use 16 megabytes if we had primitive types. We're using 52 because it's actual Java objects. And if we keep going, we have all these objects, the index objects. And if we look at their details, right, there's this index instance that has a position and a class ID. So there's 12 bytes of header on every object, and then 8 bytes for the first long, 8 bytes for the second long. That gives me 32 bytes. When I really only wanted 2 longs, right? So I wanted 16 bytes, and I'm already using 32 bytes. But then when you think about it, the position in the file, well, maybe I don't need that many. I don't need a long because maybe the file is small and the position is only going to go so far, right? So it turns out for a 160 megabyte file, I only need 4 bytes. The class ID, it's an ID. It's a reference essentially, and so ID is same thing. Like I said, they use 4 bytes on 32-bit VM, 8 bytes on 64-bit VMs. So here, the class ID does not have to be a long. It could only use 4 bytes. So essentially, we're using 32 bytes instead of 8 bytes for this. So objects, when there's a lot of them, it kind of sucks. Hash map. So that's kind of an interesting thing. There's a bunch. There's like 5 hash map arrays. We have 5 index, so you kind of get where that's coming from. And that's using 14 megabytes. So how does hash map work? Who's looked at the implementation of hash map before? I have a couple of hands, nice. So it's actually pretty simple. It's an array of linked list. That's it. So hash map is an array of linked list. Let's look at the actual details. So this is, in the hash map, you have an array of node. It's called table. And then a node has a hash, a key, and a value. So that's where your keys and your values are held. So you know how you have to implement equals and hash code. If you do that, then the hash code is run through a hash function. So hash code is an int, right? It's run through a hash function, and then it's done modulo of the size of that table, and that gives you an int, and that's the index in the table. And so that's why it's important that you implement your hash codes correctly, and you don't always return 2 or whatever. Because what happens then is a bunch of objects are going to have the same index because they have the same hash. And the first one is going to be the node in that table, and then it's going to have the second one is going to be the next on that node, and so you have like a linked list in the table. So if we kind of summarize, and the other thing that's kind of interesting about hash maps is that they keep growing as you add stuff, but they don't really have to. If you think about it, you could just keep the table a single size, and you could just add to the list. But as the linked list get longer, it becomes slower and slower to find an object because you have to go through that linked list. So typically, we use a load factor of 75%, and then the size is actually the next power of 2 of that load factor. So that's a lot of wasted space. What it means is that there's always going to be, it's important for hash map to work, to be efficient, it's important that there's a lot of empty spaces in the array. And so we also saw that the key is like here, these are objects, and so the key is an object. We want a long, we don't only care about the primitive types. All of that to say that, and this is linked list, but all of that to say that there's a lot of memory that's wasted here. So hash map is a lot of waste. Every entry is a lot of extra metadata when we just want 2 bytes or 8 bytes, I think. There's another way to build a map that does not necessarily waste as much space. If instead of being a hash map, so a hash map, you compute a hash for your keys, and that's where the entry is in the array. The other way to do that is just to create a sorted array where every key, because every key, if your key is a primitive type, then it will be able to be sorted, right? And if you have an array of sorted keys, then you can actually find them in a relatively fast. So the idea is instead of doing a hash and finding location in the array, Instead, you do a binary search. If you have a sorted array, you can do a binary search to find where the key that you're looking for is in the array. And that's log n instead of constant type, but that's actually reasonably fast. So the second idea, so let's use the sorted array. The second idea is, what if instead of objects, we just use bytes? What if we had a sorted array of bytes where every entry is just a bunch of bytes, where the first x bytes are for the keys and the next n bytes are for the values, and then we just use that. Then we don't have any object overhead. So to kind of like go through that, the idea is here we would have our array, and the first 4 bytes in that example would be the object ID, and the next 4 bytes would be the position for class instance, and next 4 byte would be the class ID. And that's it. And so then you can sort the arrays. So what does that get us? It gets us to 40 megs. So we went from 240 megs to 40 megs by using bytes instead of using objects. If you look at the details, this is sorted bytes map. It's in LeakCanary. You can check it out online. But essentially, it's just one giant array. And there's information about how many bytes for key, how many bytes for value. One of the interesting things is that when you look again, you're like, oh, but then, so can we compress that even more? We're still using 40 megs. Well, it turns out the map of strings is still using 13 megabytes, but all these strings, they're all share the same prefixes because it's package names. So I haven't done that yet, but it would be interesting to start figuring out ways to compress that. So in summary, I guess I hope you learned a few interesting things today. I know this is not your typical here's how to use a library talk. If there's some takeaways, I think one of those is don't be afraid of algorithms and data structures. Sometimes people use complicated words for things that are actually, if you're used to coding, you'll figure them out pretty easily. Use the profiler, and whenever you have memory problems, YourKit is actually a great tool, and it can give you really good insights. It's just the UX is kind of hard. And as always, don't optimize early. Start with measuring. Don't randomly change local variables to something else, or like make decisions without looking at the overall picture. And that's it. I hope you enjoyed diving into the guts of LeakCanary. I'll finish by saying I do have some LeakCanary stickers, and I'm not paid to give them to you. I'm just happy. I love the new logo. And also Square is hiring, of course, and there's a Square booth over there. So if you want to talk to us, we're usually by there. Yeah, and that's it. Thank you.